Let's start with two stars of equal luminosity. That means they make the same amount of light. But let's move one star further away gradually. You probably notice that the star is getting less bright as it moves away, even though it's making the same amount of light at the phone. Does the star being less bright mean it's further away? No, it doesn't. You can see the star on the right is less bright than the star on the left, but they're the exact same distance away from the camera. And in the next image, the brightest star is farthest away. But which one appears the brightest to you? What if the opposite happened? Would that make it more confusing? The stars in this next image have the same brightness to your eye, but the star on the right is further away. Because it's making more light or has a greater luminosity, it appears just as bright as the star that's close to you. The more luminous star was further away, but we experience the same apparent brightness. So brightness cannot tell us how far away a star is. So let's look at these two stars again, specifically this one that's moving away from us. You can still notice it's getting dimmer, less bright as it moves away, even though it has the same luminosity or is making the same amount of light. And it does that at a consistent rate. And that's important, because the further away a star is, if it's the same luminosity, its brightness decreases predictably. So if we know how much light the star is giving off in the first place, or its luminosity, we can tell how far away it is based on its brightness. But how do we know how bright a star is when it's light years and light years away from us? If we knew that, we could find the distance of the star to Earth. Even stars that are too far away to use parallax to determine their distance. That's why we're going to enter a scientist named Henrietta Swan Leavitt, who analyzed data to answer this problem using the same math that you use in 8th grade.